Okay, so let us look at some related rates problems. You can look at the attachment with this video to see, because I didn't print it out because the problems are all listed there. So here we go, problem number 1, and we'll do a few of these. A spherical snowball is pushed off the top of a really long hill. Rolling down the hill, the snowball grows in size at a constant rate of 1 cubic centimeter per second. So the units, 1 cubic centimeter per second, tells me its volume, and it's growing, so dV dt is going to be a positive 1. How quickly will the radius of the snowball increase? So I'm looking for dr dt when the radius of the snowball is 10 centimeters long. So my instant is r equals 10. So I need a relationship between volume of a snowball and its radius. Well, that is 4/3 pi r cubed. And then we differentiate both sides with respect to t implicitly. dV dt, constant, so pull it out, 4/3 pi. And the derivative of r cubed with respect to t is 3r squared times inner with respect to time. And now we can plug in and simplify. dV dt is 1. The 3's will cancel, and we will have 4 pi. The r is 10 dr dt. Notice that I did not start plugging in until after I differentiated everything. And so dr dt is 1 over 40 pi. And now for units, centimeters per second, because the radius is measured in centimeters and the time was in seconds. And there we go. That is question number 1. Done. Number 2 is similar. Number 3 is similar. Number 4 is similar. Number 5 is similar. Number 6. All right, number 6 has a diagram. So here we go with number 6. So it says that two people are 50 feet apart. So here is the 50 feet. Here is person 1. Here is person 2, and I don't know why people always stand with their arms up in the air like this. Who knows, but that's what they're doing. One of them starts working north at a rate so that the angle shown in the diagram below is changing at a constant rate of 1/100th of a radian per minute. So my d theta dt, it's increasing because this person is working north. This is 1 radian per minute. At what rate is the distance between the two people changing? So that would be this distance, because this guy is standing, or this person is standing still, and this person is moving up. So that would be this distance, which I label x, when theta is 0.5. So I'm looking for dx dt, and my instant is when theta equals 0.5 radians. Okay? So I need a relationship between x and theta. Right triangle trigonometry tells me that this would be adjacent over hypotenuse. That's cosine theta equals adjacent over hypotenuse. And now if I differentiate both sides with respect to time, derivative of cosine is negative sine theta times d theta dt equals, the 50 is a constant, I can pull it out. And this x is the same thing as x to the negative 1, so it would be negative x to the negative 2 times dx dt. And now that I have my relationship, I can start plugging in for my instant. So my instant, I have theta is 5, I have d theta dt is 1, but I don't have x. Notice that, that's a problem. But I can get x, because the instant that theta is 0.5, I can use the original relationship here to figure out what x is. So at the instant when theta is 0.5, we would get, if I solve, cross multiply, I would get x equals 50 over cosine of 0.5. So now I can plug in everything that I have. So this is negative sine of theta, which is 0.5. d theta dt is 1. 0.01, I'm sorry, 0.01. So this is 0.01. Gotta learn how to read. Negative 50 over, this would be x squared. This would be 50 over cosine of 0.5 squared, dx dt. And therefore, dx dt is equal to, yikes, well, when all is said and done, I bring this up, I bring this down, this would be negative 50 cosine squared of 0.5 over negative 50 sine of 0.5 times 0.1, I have to move it all the other side, to the negative 1. Or dx dt equals, well, the negatives would cancel, the 50s would cancel. Oh, well, it was 50 squared. 50s would cancel, and I would get 50 cosine squared 0.5 on the denominator, and in the numerator I would get 50s cancel, sine of 0.5 times 0.01, whatever that is. And then the units, we're told that they are 50 feet apart, so this is feet per minute because we're changing in radians per minute. If you want to plug that into a calculator, make sure you're in radians to find the answer. But again, we're math people, so that is an acceptable answer. And notice this problem was different than the previous in that at my instant I had to also solve for the other quantity. So that is definitely something that can happen. Let's look at some more of these. Let's see. Problem number 15. This is a little different. Problem number 15. Here we go. Do it on the back here. All right. Problem number 15. Here we go. 15. The tuning frequency f of an electronic tuner is inversely proportional to the square root of the capacitance. In other words, as f goes up, the other quantity will also go down because they're inversely proportional. Inversely proportional means as one goes up, the other goes down. So here we have f equals k over rad c, where k is some constant. F is the frequency and c is the capacitance. So we are told that when f equals 920 kilohertz, the capacitance is 3.5, I believe that's picofarads. I believe the capacitance is measured in picofarads, or in this case farads. Find how fast f is charging at this frequency. If dc dt equals 0.3 picofarads per second, we want to see how fast the frequency is changing. That's df dt. So we already have the relationship here. And so I can differentiate both sides with respect to time. This is df dt. K is a constant. This is the same thing here as c to the negative 1/2. So this would be negative 1/2 c to the negative 3/2. And now the problem is I have c at my instant, but I don't have k. But again, we can use the given quantities to solve for k. So up here, or I guess I can do it here, we have that f is equal to k over rad 3.5. So k equals 920 times rad 3.5, which means df dt, I can now start plugging in, is equal to, this is 920 rad 3.5 times negative 1/2 times c, which is 3.5, to the negative 3/2. And then whatever that turns out to be, and that frequency will be in kilohertz per second. Kilohertz per second. All right, here's where things get a little difficult. Problem 16, related rates with multiple rates, more than just two. Two taxicabs begin at the same time at the intersection of Park Avenue and 59th Street. We'll say that's right here. Park Avenue, 59th Street is right here. One taxicab heads uptown on Park Avenue at 40 miles per hour, so it's going north. The other heads west on 59th Street at 30 miles per hour, so it's going this way. Both have the unbelievable good fortune not to be stopped by traffic lights or slowed by traffic. When the taxicab on Park Avenue has gone half a mile, how fast is the distance, as the New York crow flies, between them increasing? The expression "as the crow flies" means we ignore buildings and we just draw a straight line, because a crow would be able to fly over everything. So that's the expression "as the crow flies." So what's changing here? Well, the distance from the starting point to the north, this is the displacement of the north taxicab. This is the displacement of the west taxicab. And z is the distance between them as the crow flies. So let's see, what do we have here? We are told that the taxicab is going north at 40 miles per hour. So since this is y and it's increasing as we go further up, this distance increases. We have that dy dt is 40. And we have that dx dt is 30, because as we move further to the left, this x gets bigger. It doesn't matter the direction, it matters what's happening to the quantity. And this distance from the starting point to the left is getting larger. So dx dt is positive 30. And we want to find dz dt, question mark. And our instant is when the taxi cab on Park Avenue has gone, which is this north one, half a mile. So when y equals 1/2. So here we go. I need a relationship between x, y, and z. We have it, the good old Pythagorean theorem, or some people call it the Gogu theorem. You can look up who Gogu is. If we differentiate with respect to time, this is 2x times dx dt plus 2y times dy dt plus equals 2z times dz dt. Sorry about that. And to make life easier, I will divide this entire equation by 2 and just get x dx dt plus y dy dt equals z dz dt. So now I have this relationship. The problem is my instant, I only have y, and that's 1/2. I have dx dt and dy dt, so I have this, I have this, I have this. We want this dz dt, so I still need z and I still need x. So the question is, how do we do this? And the answer is that we need another relationship that you might remember. And that is that distance equals rate times time. And if you don't remember that, or don't understand why that is, think about how these things are measured. Distance could be measured in miles. Rate is normally miles per hour, and time is in hours. And if you cancel the hours, you get miles equals miles. So that's how I remember distance equals rate times time. Or you can think of it as dirt. So yeah, dRT. So whatever. In any event. So we're going to use this. So we know that the instant we're looking at, y is 1/2 and dy dt is 40. So using this, we get that, and dy dt, yeah, is 40. So we know that the distance is 1/2. The rate that this cab is traveling is 40 miles per hour, and it's gone 1/2 mile. And so I can find the time. I can find that the time is 1/80th of an hour. Now, how does this help? Well, I can now use this to figure out what x is at that time, because x will be the rate, which is 30, times the time, which we found was 1/80. So x at this instant is 3/8 of a mile. So at this instant, I get 3/8 of a mile. And on top of that, I have that x squared plus y squared equals z squared. So now I can figure out what z is. Do that over here. Since x squared is 3/8 squared plus y squared is, well, I'm going to write it as 4/8 squared equals z squared. And if you notice, this is a 3, 4, 5 right triangle, except it's 3/8, 4/8, 5/8. So z is 5/8 at my instant. So now that I have everything, I can plug it in. X is 3/8. dx dt is 30. Y is 1/2. dy dt is 40. Z is 5/8, and dz dt is dz dt. And when I solve this, we get, let's see, this is 90/8 plus 20. All times 8/5 equals dz dt. Those 8s would cancel, and I would get 90. That would be 160 divided by 5 is 32, I think. Equals dz dt. Did I do that correctly? I might have messed this up. I think I might have messed this up. 122 is dz dt? No, that's not right. It should be 50. I messed up somewhere. Let's see. 90/8 plus 40/2 is 20, and then multiply by z is 5/8, x is 3/8, dx dt 30, and y dt 40. Let's see. What if I make this 4/8? That's 160/8. There we go. That's better. I don't know where my arithmetic messed up, but I messed up somewhere. This is 250/5, which is 50, which is dz dt. Sorry about that. So dz dt is 50 miles per hour. Now, I'm not sure where my algebra messed up before. 1/2 times 40 is 20. 90/8 plus 20 times 8/5 90. Oh, because, I forgot to do the 90 divided by 5 over here. Okay. It comes out to 50 miles per hour. Sorry about that. But again, notice we had 3 rates, and we had to recall that distance was equal to rate times time. Here's another problem, problem 17, that's very similar to this. So here we go, problem number 17. A 15-foot ladder is resting against a wall. So here's my 15-foot ladder, 15 feet. Here's my wall, okay? The bottom is initially 10 feet away from the wall and is being pushed toward the wall at a rate of 1/4 feet per second. So this distance is changing as the ladder gets pushed toward it, and dx dt is negative 1/4, because as we push the ladder toward the wall, the x gets smaller feet per second. How fast is the top of the ladder moving up the wall? So we need dy dt, if we call this y. 12 seconds after we start pushing. So my instant is t equals 12. Okay? So let's see. X squared plus y squared equals 15 squared. 2x dx dt plus 2y dy dt equals 0. This is similar to the previous problem, except the ladder isn't changing. Cancel the 2's. And now let's see. I only have at my instant when time is 12. So that doesn't help too much. But again, I know how fast this is going, so I can figure out how far the ladder has moved since. So let's see, how far will the ladder have moved after 12 seconds? So let's see, the distance that the ladder will have moved is rate times time. So the distance will be negative 1/4 times 12 seconds, which is, it will have moved 3 feet. And since it starts at 10 and it loses 3 feet, at this instant, x would be 7. So now I have what x is at that instant. And then I know that the ladder is 15 feet, so I can figure out what y is, because x squared plus y squared equals 15 squared. So 7 squared plus y squared equals 15 squared. That's 225 minus 49. 225 minus 49 is 176, I believe. Yep. And then the square root of 176 is the square root of 176. It's not nice. So I'm just going to leave it as the square root of 76. So then we have 7. Dx dt is negative 1/4. Plus y, which is rad 176. Dy dt equals 0. So dy dt would equal 7 over 4 rad 176 feet per second. Voila, and we are done. And that is problem 17. And there are others that we can look at, but I just wanted you to get a preview of how to do a bunch of these problems, because you're going to try a few of them. And then tomorrow in class, we're going to look at 2 very, I don't want to say famous, but problems that anyone that thinks of calculus thinks of. They are the shadow problem and the cone problem. And those are 2 problems that we're going to look at. So I hope you enjoyed this video, and I will see you in class tomorrow. And because this is related rates, you get the grandpa seal of approval, because he is a relation. Bad puns upon bad puns. Thank you for watching, everyone. Bye.